Well, today, actually, what we're going to do is look at the stepper motors. So you have a assortment, maybe 3 stepper motors, maybe 4, depending on what printer you have on your printer. And it's a good idea to know how they work. So we're going to do that. We're going to start with kind of a very simple model of a stepper motor. So this stepper motor is what one would look like. You know, these little guys. This one's called a NEMA 17. The 17 has to do with the diagonal distance between the mounting holes. It doesn't have anything else related to it. But there's other versions, but pretty much all of these style printers use NEMA 17s. Some of them might be shorter. Some of them might even be a little longer. But they're all NEMA 17s because of the pattern for these mounting holes. And the purpose of the stepper motor is to accurately deliver steps or turns or partial turns of this shaft here. Most of the stepper motors in 3D printers have 200 steps per revolution, so it takes 200 little increments to go around one revolution. So that makes them like 1.8 degrees per step. And then you also have some kind of lead screw or a belt or whatever attached to it to do the actual movement. We'll look at this lead screw in a minute because most of your x-axis, your thing that moves up and down, is going to be controlled by something like this. There are a few printers that use a pulley system to raise and lower the bed, but most all the ones that you're going to be dealing with have some kind of lead screw like this. Maybe not this exact one. They have different pitches and such, but have something like this one on it. Or some of them have 2. Some of them have 2 dual lead screws on the z-axis. But let's do a little simple version of what's inside one of these stepper motors. So there are permanent magnets on the rotor, the inner part, the part that rotates. And I'm going to draw them a little different than what's actually going in the stepper, just to make the explanation a little simpler. But let's assume it looks like this. That you've got. Oh, I don't want. Well, we can keep that one for later. Oh, no, it wants me to move that one. Okay. Let's use that. So these would be permanent magnets, not electromagnets. They're always one or the other. We'll just say for what we're going to do here that half of it's north, half of it's south. That's not how they work in the stepper motor. But we'll look at that later once we get the general idea of what's going on. So there's some permanent magnets in here. So this guy's permanent. And there are some electromagnets in here. So we'll do those like this. You know, little coils of wire around some kind of core. You run current through it and it produces a magnetic field. And we'll say that these are a set. So this, maybe I should make them in color so that we can see that they're a set. So this will be a set. And let's do green. Green will be a set. So those are electromagnetic coils. And you can energize them in such a way. So one way we could energize these would put a south pole down here, a north up here, and a north south. So that, I guess it doesn't matter what's going on over here. Let's just look at what's going on at that end. So that would kind of lock the stepper motor in place as it is. It wouldn't want to move. And the green ones aren't even energized at all right now, so they're just off. And so you can tell that kind of thing is happening when you do start, maybe after you home your printer, then nothing wants to move. Like you can't, right now I could move the printer all around just manually. But once you home it, then it kind of locks it in place and you can't move everything. That's some combination of all the coils in your stepper motors being energized to hold its position. Now, stepper motors don't, the ones that we're using, they don't have any kind of feedback to the control system. So they don't tell the system that, yes, I actually moved or I'm actually at this rotation or anything. Maybe if you use some standard servos, they kind of hold a certain position. These don't hold positions. They just they hold where they are at. They don't know that anything about where they came from. They know where they should have been. So it's all kind of this dead reckoning thing where it assumes that you've told it to take 30 steps and it actually took 30 steps. It may not have done that at all. So to take a step, you could turn off the blue ones and then turn on the green ones in this pattern. And that would make the little core here want to take a 90-degree step. So that's a pretty big step. You know, yours are taking 1.8 degree steps. This one is going to take 90-degree steps. So 4 steps makes a revolution for this one. And so you could keep changing the pattern of how you energize these coils to make it step around. You can take half steps, so a little bit more complicated to take a half step. But let's say that we want it to end up here. So instead of taking full 90-degree steps, we want it to be at a 45-degree. So if I energize this one and the green one to south, north, and north, now I've got both coils energized. So I'm actually having to deliver a little bit different power scheme, but I could kind of do a half step, and that's not too bad. So if you can usually enable half stepping or even what's called micro stepping. So you could do a micro step where maybe you go in. Whoops! Didn't want to erase the actual core. Let's put it back. So half stepping, you energize both of the coils here. Micro stepping, you do the same thing, except maybe, let's see, we want it to end up something like this. So north and south. You energize them partially. So in this case, it looks like the north is closer to the green side. So maybe this is a south, this is a north, and maybe this one is a, I don't know, half of a south and half of a north. So you energize them at different levels. Instead of giving full power to the green and blue to make the half step, you give proportional power to the different coil sets to give these micro steps. So the smaller the micro steps you start trying to take, the less accurate it's going to be, because you're relying on, there's no feedback in the stepper motor that tells it it's actually at one of these positions. You have to assume all of this happened, and so it gets kind of complicated on the micro stepping. And how that could hurt you is if you're trying to do micro stepping on your printer, which, you know, maybe there's some reason you want to print really tiny layers or something like that, then you have to do micro stepping on some of these printers. And then you get a little bit less accurate holding power. There's a certain holding torque associated with these stepper motors, and when you start changing the power scheme of how you're delivering the electromagnetic power, then it gets a little less accurate. So this is similar to what's inside the stepper, but let's actually look inside this. I took this one apart so that we could look inside of it. So it's just 4 screws on the front on most of these is all it is. Actually, I think they actually go through the back, and I don't remember which way it was. I think they do go through there. It just goes through the whole way. But you can then take it apart. And so there's more coils inside here, but there's still only 2 sets. So out of most of your stepper motors that you have, there's 4 wires coming out. I actually think this one has like 6 plugs. Yeah, but only 4 wires come out of it. And that's to combine, you know, maybe this is the green set and blue set and red set and orange set or whatever. I think these have a black and green pair and a blue and some other color pair wire on it. I don't remember. But there's 4 wires that control those electromagnets. And there is a permanent magnet core, if I can get it out of there, but it looks different. Oh, wow. And it is a permanent magnet, so it gets stuck in there. There we go. Oh, there's a little wave washer underneath it to kind of space it out. We'll put them back in there. All right, so this, let's see, we'll have to get pretty close to see all of what's going on there. Let's see if it'll focus. All right, so here I can see, yeah, you can even see it up there. So, all right, so first of all, there's all these little lines. So in this one, I've got two separate, some of them have more, so you can get more holding power if you have more of these cores in here. But the whole core here, maybe this whole side or this whole front piece is a positive or a south pole magnet, and this one's a north pole magnet versus how we drew it on the screen here, where half and half of each core was north and south. This one, this whole thing is south and this whole thing is north, or vice versa. I don't know which one it is. And it's got all these little ridges on it. Now, if you look really close, you can see the little layer lines in there. These are actually stacks of little discs, little magnetic discs that are all stacked together. I don't know how many there are. 1, 2, 3, 4. Like 20 discs stacked together to make one of these pieces. And they have all these little ridges around the outside. There's 50 of those ridges on one of these cores. And let's see, we can make it, yeah, you can see they're not lined up. See, the back one, the little ridges are in the gaps of the front one. And so that helps align the electromagnets and the permanent magnets. Inside here, there's a match, well, not exactly matching, if I can find them in there. There they were. Well, you can see that there's sort of matching. There's 48, I think, of the ridges inside here. Let's see, 1, 2, 3, 4, 5, 6, and there's 8 of those. There's 48 ridges inside there, so they don't ever line up to where they would lock one to one. There's always some that are off. And so you can change the same idea here. You can turn these to, see if we can draw something like what's going on in there. So you've got on the core, you've got something that looks like this. And maybe this is a south pole. And then on the electromagnet side, you've got a pattern that's similar. And you can change it to north and south. So when it's north, then the little ridges would line up. And when you change it the other way, they would line up with the gaps. Oops. So the core doesn't change, it's still a south. But when the electromagnet is a south pole, then the little ridges line up in the gaps, so that it's repelling as much as it can and attracting when it can. And there's really tight tolerances in there. Like if I put this thing back in here, you can't really see down in there where the ridges on the electromagnet are, but you can kind of see they're really close together. And it's not centered. It won't center until I put there's a bearing block in there. So it won't center it just on its own. It's going to be touching somewhere. But that's kind of what goes on inside these stepper motors. It's just an alternating pattern of which one of the coil sets are you going to turn on at any time. And with the 50 different ridges on there, you can get 200 steps per revolution. And that's pretty standard on the NEMA 17. Oh, and the 17, I said that, but here I can show it better now. The 17 is 1.7 inches on this diagonal is the 17 part. So what that does for your X and Y axis is not as, you still want them to be correctly calibrated so that they're moving in the X direction as far as you tell them to move and all that. It affects the Z direction probably the most, because pretty much the X and Y, these, there are no, you could do partials, half steps are not too bad on these things to get down to 0.9 degrees per step. The micro stepping is where the power issues start to, it gets kind of, you really need that kind of tiny step anyway. But on the Z axis, it matters because that controls your layer height. So if you can figure out what the ideal layer increments are for your printer, then you can print in those increments. So what you would have to do for that is you'd have to look at your lead screw. Well, you'd have to know, do you have a 200 step per revolution motor, which pretty much all of you do, unless you have a special setup, then, which there are some of these stepper motors that are like 400 steps per motor. So they just have more little ridges in there. So there are other ones. I'm pretty sure that any printer that you bought for this class, it's just like this one with 200 steps per motor. The only difference may be on some of the, particularly on the y-axis. It's a lot of time, or to the x-axis actually, the one that moves the print head. It's usually the one that needs the least amount of power, and so sometimes they'll be thinner than this. So there won't be as thick of permanent magnets inside there, and so they can make it a little smaller, and it doesn't have the same holding torque because it's all smaller. But you don't need as much when you're just moving the little carriage around. So some of these Bowden tube printers, they don't have a lot of weight to move around, a lot of mass that moves around in the X direction, so they might have a thinner version. It's still an EMA 17, but they might have a little bit thinner this direction version. Pretty much all the others have this exact stepper motor of whatever brand, but this motor. Sometimes on the printers that only have a single Z-axis, it will actually be longer to lift up the print head and everything. But pretty much this is the most common kind you're going to have. So what you would need to do if we were thinking about Z-axis layer increments and only using full steps. So you don't use any of the ones where you're delivering different amounts of power. Everything's the same amount of power. That way it's more predictable. And what you need to know is you need to know 200 steps per revolution from your stepper motor. And then you have to look at your lead screw. And there's a couple of different kinds. Oh, well, they're all the same type of thing, but a couple of different profiles for the screw itself. So this one, and a lot of them, not all of them, in fact, yeah, the one on this printer, this Tarantula Pro, is different from this one. I can't see very well. It's all shiny. I think this is a double start. I think that's a double start. This one is a quad start screw. So what that means is if you were to trace one of these, let's see if I can do this. So we'll paint this thread with this Sharpie. All right, there it's coming back around. I can see it. I don't know if you can or not. Yeah, you can see it. See, I traced one thread, but I skipped 3 in between there. So there's actually 4 threads that are all happening at the same time. Sometimes it's called a 4-axis screw or a 4-start, quad start, whatever. There's 4 threads that are all lined up together, but they have a really big pitch, but it makes it look like it has a very small pitch. So what it does is when you turn it 1 revolution, in this case, it would move 4 times faster than, in this case, in this direction, it would move 4 times faster than what it appears it would by just looking at it. So what we would need to do is figure out, and I've already done this, so I don't have to. Everything's in millimeters over here, so we would have to figure out, find some place where some of these line up easily, and pretty close to at 1 or at 0 millimeters and at 35 millimeters, those line up with 2 thread patterns. There's some other 60 also kind of lines up, so there's some of these that relatively line up evenly, and you count the number of threads. And when I counted them, it was, I've forgotten, I think it was 18. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 18 threads per 35 millimeters. So we know that now. Let's go over to here. So in 35 millimeters, there were 18 threads, but we have a quad start, so we'll do it a 4x thread pattern here. So there's actually Oh, I need a calculator. Here's one. So 18 threads with a 4 start is 4.5 revolutions. 4.5 revolutions. If we had 18 threads, but it was a 4 start, that would be equivalent to 4.5 revolutions. And in those 4.5 revolutions, we would go 35 millimeters. So 35 millimeters per 4.5 revolutions is 35 divided by 4.5, 7. And there's a lot of decimals back here that I'm having to ignore. So 7.78 millimeters per revolution. So for this lead screw, you travel 7.78 millimeters, and maybe you round it to 7.8, I don't know. But 7.78 millimeters in one revolution of the screw. When you combine the number of threads it has, but it's a 4 start or a quad start lead screw, and we measure off how far, 18 threads covered 35 millimeters, but it's a 4 start, so that's 7.8 millimeters per revolution. But our stepper motor has 200 steps per revolution. We can combine this and this to get how many millimeters per step. So if we want millimeters per step, 7.78 millimeters per revolution. And then we will want to cancel out the revolution. So 200 steps per revolution, those will cancel out, and I'll have millimeters per step. So divide by 200. And I get 0.039. I'm going to just say that's 0.04 millimeters per step. And we rounded a couple of places, so if I want to only do full steps on here, then I should probably have, for this stepper motor and this lead screw that we just measured, I should probably have 0.4 millimeters per step. So let's go to configuration.h, and we're looking for Z steps. So E steps we looked at a couple of weeks ago for the extruder steps. The extruder steps is something that you actually should calibrate, because it's the one that could be a little bit different from printer to printer. They come with whatever's a really close number built into them, but you probably did want to calibrate that one. X and Y, unless you print a calibration cube and it's nowhere near the 20 millimeters or whatever you printed, then I wouldn't bother calibrating those. And I wouldn't calibrate Z either, but you can use Z to, you can use what we just did to, like we figured out, for that combination of lead screw stepper motor, I should print layers in increments of 0.4 millimeters. So 0.2 millimeters would make sense per layer height, but 0.18 is not, it would have to half step to get to there. The next one down would actually be 0.16 according to our 0.04 layer increments. And all of your printers are going to be different from that potentially, because you might have a different lead screw that has, maybe it's not a 4 start screw, it has a different pitch on it, different lead, and so your printer might be different. I still haven't found Z steps yet. I might have to search for it. Let's see. Why don't we just do that? Control F. So we're looking for Z. Oh, I don't remember if it has an underscore. I think it does. Let's see. There it is. All right. So steps per millimeter settings, and it's in here with X, Y. This one has 2 extruders set up. It says that there are 400 Z steps per millimeter. Now, I think that's not going to match up with what we just did, because we just calculated that there are 0.04 millimeters per step. So 1 divided by 0.04, we actually have, for this setup, our Z steps would need to be 25. And so when you tell it that, now it knows this, and the units on this are steps per millimeter. So I just took 1 millimeter and divided by 0.04. I think for this tarantula, it's like 1600 because of the lead screw that it has on there. And so depending on what you have for your lead screw and your stepper motor, although you probably all have the same stepper motor, then this number, Z steps, is going to be something between probably 25 and 1600. All right. So if you go in, on this one anyway, if you go into control motion, it has steps per millimeter down there. So off the screen, it's covered up though. There we go. Now it's all washed out. But you can see Z steps 399.29 is what's in there. So they actually kept some of the decimal places. But that 0.29, it means that you have to do some kind of partial stepping because they don't have it set up for 4 steps. That 0.29 is not a 4 step. So I think it's better if you can figure out the actual steps per millimeter. But if you are constantly having issues, like you really need to print accurate parts and they're just not coming out the correct shape, then that's how you can adjust for the changes in dimensions X, Y, and Z. Probably it's not the first thing to do. And it's probably true that you'll never actually get perfectly accurate parts with 3D printing of this style 3D printing because there's no feedback in the system. There are currently, as far as I know, no printers, none of these style printers anyway, that measure the amount of filament that actually exited the nozzle. It's all based on how much you assume you put in, and the filament itself is going to be, it's not this bad. It actually kind of used to be this bad. But you assume that the filament, or well, not you, but the printer and the slicer and all that, they assume the filament is perfect, right? But what you actually get is like this. And some places it's a little bit, oh wow, that's not what I wanted. That's not at all what that's on. Some places it's a little bit wider, some places it's a little bit thinner, and the printer doesn't have a way to know that. It doesn't measure the filament as it goes through any point. It doesn't measure what comes out of the nozzle. It's all based on basically mass in equals mass out. And so there's calculations of you put in what this nominal diameter is assumed to be, so 1.75 millimeters is what the default kind of is for most of your printers. And then it does all of its extruding based on what that assumption is. And I wouldn't, if I was having slight issues, like I printed a calibration cube and it came out 19.85 millimeters in one direction and 20.25 in another, I probably wouldn't worry about it because you're probably not going to get much closer. But if it came out in the 18 millimeters or 22 millimeters or something like that, the first thing I would actually check is all the belt tension. The belts probably need to be tighter than what you think they are. They should be pretty tight. And if you're having trouble tightening, your X or Y belts, then there are some belt tensioners. There's some pretty simple ones, and then there's some more elaborate ones. Let's see if we can find some decent ones. Thingiverse has been really slow lately. In fact, they had a message on their webpage that we're sorry it's really slow, but they are a pretty useful site for, currently working on performance issues. But belt tensioner, let's see, there's these super simple ones like this that if you just can't, maybe you've already attached the belt and your printer doesn't have an adjustment, anything that slides or makes it tighter, you can just put one of these, print one of these, or even this one's, it's not adjustable, but there are some like this that are adjustable. They have a little screw in there that let you tension the belt. So you could put one of these on there to tighten up a belt. Let's see if I can find one of the more elaborate ones. But that's super. I mean, even your printer, even if it has a loose belt, could print that. Here's one that's one of the more elaborate ones, where it actually replaces the end of the axis. I'm sure Amazon makes metal versions of the, or not Amazon, but they sell them on Amazon. Here's the slowness of Thingiverse. This little thing adds a knob where you can actually tension the belts for, it looks like it has one for X and Y. Much more complicated print, but if you really want to get the belt tight and you can't do it any other way, then these are relatively easy ways to do that once you get the print made. Those would also count on the printer upgrade assignment if you wanted to do one of those. But that's where I would actually start, is at the belt being probably too loose. And then the next thing I would do is adjust the printing speeds, particularly the accelerations in the slicer. And then if nothing else, if you're still way off, then maybe somehow your stepper motor firmware combination isn't producing the right number of steps for the expected amount of movement. And you do need to go into your firmware and change them. I think I could probably change them from the panel. I don't know. Let's see. I never have tried. I'd like it to not be so washed out, though. I don't know. It was better. I get the right angle for it. You can actually change these screens if you wanted to. Let's see. Control, motion. Let's just see if I can. Yeah, you can change them by, in this one, 0.1 millimeter increments, or 0.1 steps per millimeter increments. Remember, any changes you make on this panel don't get saved unless you go in and store settings. Normally, you have to initialize EEPROM before you do any changes. So initialize it, change stuff, and then store the settings. Or they won't, whenever you turn off the power, then they'll go back to the way they were before.